Welcome back. In our last episode, we wrapped up altimetry by reviewing how pressure settings and altimeter accuracy affect safety. Now it's time to explore one of the most fundamental forces in meteorology: temperature. It's not just about being hot or cold, temperature drives everything from air density to turbulence to thunderstorms. Let's start with the basics. Temperature is a measure of the average kinetic energy of air molecules. Warmer air has faster-moving molecules, while colder air has slower ones. This motion affects air density, pressure, and moisture capacity, all of which matter in flight. As air warms up, it expands and becomes less dense. That means fewer molecules per cubic meter, less oxygen, less lift, and reduced engine performance. On the other hand, cold air contracts, becoming more dense, improving aircraft performance. This brings us to the concept of lapse rate, the rate at which temperature decreases with altitude. In the standard atmosphere, temperature drops by about 2 degrees Celsius per 1,000 feet. But in real life, the lapse rate varies due to weather systems, terrain, and time of day. There are several types of lapse rates. The environmental lapse rate is the actual temperature change with height in the atmosphere at a specific time and place. It's measured using weather balloons and is key for understanding stability and cloud formation. Then there's the dry adiabatic lapse rate, the rate at which unsaturated air cools as it rises, roughly 3 degrees Celsius per 1,000 feet. If the air contains moisture, it cools more slowly. This is the moist adiabatic lapse rate, around 1.5 degrees Celsius per 1,000 feet. Why does this matter? Because lapse rates determine stability. If rising air stays warmer than its surroundings, it keeps rising. This leads to instability and the formation of clouds and thunderstorms. If it cools quickly and becomes colder than surrounding air, it sinks, leading to stability and calm conditions. Temperature also plays a key role in air density. As we saw in our density episode, warmer air equals lower density equals reduced lift and engine power. That's why performance charts always account for outside air temperature, OAT. Let's look at a practical example. You're taking off from a high-elevation airport on a hot day. Even if your pressure altitude is 5,000 feet, the density altitude might be 8,000 or more. That means your aircraft behaves like it's taking off at 8,000 feet, longer roll, slower climb. High temperatures also affect engine performance. Piston engines rely on air intake for combustion. If the air is warm and thin, combustion is less efficient, reducing power output. Turbocharged engines help, but they still perform worse in hot, high-density altitudes. For turbine engines, temperature impacts thrust. High temperatures reduce air mass through the engine, which means less acceleration and slower response. This affects takeoff performance, especially in heavy aircraft operating near maximum weight. Pilots use performance charts to calculate takeoff distance, rate of climb, and cruise speed based on temperature, pressure, altitude, and aircraft weight. Always input the correct OAT, because even a few degrees can make a big difference. Let's talk about temperature inversions. Normally, temperature decreases with altitude. But sometimes, a layer of warmer air sits above cooler air. That's an inversion. These can trap moisture and pollutants, creating fog, haze, or smog, especially in valleys or urban areas. Inversions can also trap turbulence. If the air below is unstable but capped by a stable layer, rising air hits the inversion and flattens out, creating mechanical turbulence, wind shear, or even low-level wind shear near airports. You might encounter an inversion during a morning departure, especially after a calm night. The surface cools quickly, but the air aloft remains warmer. The result? Poor visibility, shallow fog, and a bumpy ride until you climb above the inversion layer. Temperature also influences icing conditions. In moist air, if the temperature drops below 0 degrees Celsius, supercooled water droplets can freeze on contact with the aircraft, forming ice. This is most common between 0 degrees Celsius and minus 15 degrees Celsius, especially in stratiform and cumuliform clouds. Even on the ground, surface temperature matters. Runway friction changes dramatically with snow, ice, or wet conditions. Pilots must adjust their performance calculations to account for braking action and reduced acceleration. Let's go back to atmospheric structure. Temperature helps define the different layers of the atmosphere. The troposphere, where weather occurs, is defined by decreasing temperature with height. Above it, the stratosphere sees temperature increase with height. The tropopause is the boundary between those two layers, and it's also where jet streams often form. Temperature contrast between air masses at this level fuels the high-speed winds we rely on for transcontinental flights. Knowing the tropopause height helps with turbulence avoidance and fuel planning. It varies by latitude and season, higher over the equator, 55,000 feet, lower at the poles, 25,000 feet. Pilots should check FL winds and temperature charts before cruising. Temperature also plays a role in thunderstorm formation. Warm surface air, rising rapidly, can form towering cumulonimbus clouds, especially if the lapse rate is steep and moisture is present. Strong updrafts, hail, and lightning follow. So how do we measure temperature in flight? Aircraft are equipped with OAT sensors, but they're affected by RAM rise, the increase in temperature due to air compression at high speeds. That's why some systems show total air temperature, TAT, or RAM air temperature instead. Pilots use OAT primarily for performance and icing calculations. For example, descent through freezing levels requires knowing the actual temperature to anticipate ice buildup or adjust anti-ice systems in time. Modern systems also factor in SAT, static air temperature, used for flight planning and high-altitude cruise performance. This is especially relevant for jets operating near the tropopause, where small temperature changes affect max speed and fuel burn. Let's not forget the role of temperature in atmospheric stability. Rapid surface heating after sunrise can create thermals, generating bumpy conditions in the lower atmosphere. Great for gliders, but not so fun for passenger comfort. During early morning or late evening flights, temperature gradients are more stable, leading to smoother conditions. That's why many pilots prefer flying during these windows: less turbulence, better engine performance, and clearer air. Temperature also influences dew point and relative humidity. As air cools to its dew point, moisture condenses, forming clouds, fog, or dew. Understanding this helps predict visibility, cloud bases, and the likelihood of weather deterioration. Let's recap what we've learned. Temperature affects air density, lift, engine power, and aircraft performance. Lapse rates determine stability and cloud formation. Inversions and icing create operational challenges. Surface temperature matters for takeoff and landing. High-altitude temperature affects fuel burn, max speed, and turbulence. In our next episode, we'll continue with temperature, Part 2. We'll explore adiabatic processes, heat transfer, temperature charts, and how temperature variations shape real-world weather and flight conditions. Don't miss it. See you in Meteorology number 13, Temperature, Part 2.